Hi guys, today we will be learning about database indexing. One second, yeah. Database indexing, this is one of the important topic in the databases. So, yeah. So, what database indexing is? You might have known, yeah, in front of many books, you will see the index which helps you in the faster access to the chapters. So, similarly to faster access to the rows, we keep creating indexes for the database tables. So, we can see, so let's say first let's see normal definition of what an index is. So generally we build a data structure on top of a table. It's a data structure which improves speed of data retrieval. We can say like it's a sorted copy of selected columns with pointers to actual rows. So whenever it is a sorted copy, you can do a binary search and you can access anything in the OAuth login. So basically it does of OAuth n2 OAuth login, right? So what type of indices are there generally? Let's delete this as of now. Yeah, first thing is binary tree index or B tree index in short. How does it look? So yeah, mm, okay. So it will be 50. Sorry guys, sorry. Okay, leave it. 50, 25, 75, 10, 30, 60, 90, 10, 30, 60, 90, right? So actually there will be lines between here, so this tool is not so helpful in that thing, I think. Yeah, wait 1 second. Oh man, yeah. See, I think I need to, yeah, select all these things every time. 1 second, sorry for that. Yeah, so something like this, it looks something like this. So let's say these are the user IDs, 50, 25, whatever they are. And whenever you want to search where is the where is the username of the user ID 30, what you will do first to find the user ID 30, generally it takes OAuth in, like it needs to do the linear search among all the user IDs. But here it will do a binary search and find the user ID, and this user ID points to its actual user, uh, points to the row where it is actually stored. So then we can say the whole process is optimized. So if we see pros of binary tree index, first thing is it is very efficient in queries where we try to find equal to or range queries or between, yeah, whatever, they are all the same. So yeah, and this binary tree is self-balancing. So whenever a new element enters, it automatically balances. So that data structure is like that, so that the order is maintained. Now if we see the cons, obviously overhead on writes, because after every overhead what happens, like sorry, after every write the index should be updated. For index updation the whole nodes will be changing. So this is one overhead. We call it as tree rebalancing. And for full text search it is not ideal. It's better to use some other index or something like hashing, something like that. So now one more thing here will be hash index. Yeah, this hash index is very simple. So I need some shape. Yeah, okay. So how hash index generally looks is like yeah, 1 second, please be patient. Shit. Okay. Yeah. So one more thing is this. So this is hash function, and what we will do is like we will take a key and pass it into hash function, and this hash function will give us some value, this whatever value is there. Let's say this is bucket 0, bucket 0, this is bucket 1, this is bucket 2. Yeah, and now whenever you hash them, so whatever hashes are created internally, they are also formed some, like they'll also be forming some kind of index like tree or something else. So that is not scope of this. So yeah, so generally we know that hash functions are very fast, like hash lookups are very fast. So similar thing is applies here. So generally hash functions will be O of 1 equality lookups, right? We can study about that in further videos, but about hash, but not in this. But please keep in mind that hash lookups are O of 1. Very fast for exactness, sorry, very fast for exact match. And yeah, cons, if we see, cannot do range queries or order by queries. and not supported in all DBs. Now one more thing comes is composite index. This is nothing but multi-column index. So what happens here is, let's keep a table, man. Yeah. Sorry. Yeah. Sorry, we just need 3 rows. Sorry, command it. We shall delete this. Okay, sorry, we'll keep them like that only. We shall work on only these first 3 things. And what the let's say, yeah, last underscore name, and this name would be first underscore name, and this would be row. So consider only first 3 rows. Please don't look at last five columns. Sorry, I was telling rows. So sorry, my bad. So let's say you created index on last name and first name. Sorry, this didn't change. Yeah, first underscore name. Sorry. So let's say we do index on first 2 names. Sorry, last name and first name. What happens is like, uh, it doesn't basically create 2 indices on 2 separate names. It creates one index only. It works in a way that such that whenever you are querying, the order matters in that query. Then only you can use full potential of that. Let's say you created an index on last name and first name. And if you query something which includes where first name equals to something, this doesn't work, or this will work, but this doesn't help. That indexing will doesn't help here because there is no index directly on the first name. So something like this will be helping. Something where last name equals to something. Yeah, this works. And what's the use of keeping 2 columns in the same index? Yeah, now comes the thing. Let's say you did something like where last name equals to something and first name equals to something. Here what happens is like, first it filters out the last name, and in the first name again it will search a small index kind of thing is built on that filter last name, and it can search among them very effectively. So the order matters, left to right. Order is left to right. Well, left to right. Now full text index, one of the important thing. Full text index, this is not similar to traditional indexes. It's some different kind of thing. Whatever we shall talk very less about this. So let's say you have a paragraph and you want to search a sentence. Let's say you have a very big document and you have to search a sentence. So what happens here? This normal indices doesn't work because the sentence can be too long and all that. Hashing also might not work properly on that long text. It will work, but it might take long time. It might not be that efficient. So what happens now? So there is one indexing method, like where the whole document with all those sentences is break down into words and like something called tokens. And on that, I mean, what we call whatever we have done there. So for all, there will be many documents, right? We need to find in which document this sentence is. What we'll be doing now? So some kind of relevance scoring will be done. So this thing is not part of this, but the index. One thing we can tell is like the whatever is there, the index size is very big because we are taking all the tokens and we are storing all the tokens and their frequency in the document and all these things, right? So obviously this will be very much large in size and very much complex also. Yeah. Now if we see index selection also, it plays major role. You can't select all the columns as an index, right? You can select, but that doesn't make sense if it doesn't work correctly. So good candidates for indexing is like first thing is primary key. Obviously, primary key is always unique, and on all unique things, it works very well. And one more thing is like on primary key, the database directly indices without our index query also. Like no need to explicitly mention to index the primary key. And one more thing is like foreign key. And one more thing is like wherever you are trying to use where. Let's say you want to use where on last name. You can wherever there is a scope to use where you can index those columns. And similarly order by. And one more thing, you can index those things which have high cardinality. Cardinality means the number of unique values in them, like email, username, all these things. High cardinality. Low cardinality example is like true, false, like male, female, gender, all these things. Because if you see them, you are having only two things. Binary tree on that thing doesn't work that well. So yeah, poor candidates we shall discuss. First thing is low cardinality. We should not never do. I told example just now. Frequently updated things. Frequently updated columns. If there are frequently updated columns like views count, last active or last updated, those things it creates always you need to rebalance the index. All these things happen always. There is a for every write there will be some lag or whatever overhead. So that's the backlash there. So for small tables generally no need of indexing and all that stuff. Whenever you think the database is very large and the query becomes really slow, then you can try using indexing. Or if you know that the database won't grow that larger, no need of using the indices for the small tables. And for the columns which are never queried, and small tables, right? For the columns you are never querying, if you do that indexing, what's the use? You will get overhead right, and what else you will get? Unnecessary storage for the index. Yeah. So yeah, So whenever there is something like our what we say, whenever they're in production or somewhere or whatever you're working on the table, you find the query is very slow, or whatever your query, you want to know which indices it is using, which indices it is not using, or it is doing some index scan, or is it doing normal scan, or whatever. For normal scan we call it generally sequential scan. You want to know what is happening in the query. In that case, we can use explain keyword in front of query. It gives the exact whatever we say log statements or something kind of thing, so that you can analyze what is it doing. So if you use one more keyword, explain analyze, it also gives time also, like how much time is it taking for this step, something like that. So this is some of the useful thing. So one more thing is like, let's say we built an index on, one second, built an index on let's say email, a simple email can have, let's take name. When we built an index on name, a name can have capital letters, small letters, all these things, right? But whenever you are querying, if you include where lower of name equals to something, then here that index will not be used, it will be your. So what such generally people confuse here, it is obvious, right? So index is built on capital and small words containing small capital and small, it's not built on only small letters. So the best thing we can do here is like, while indexing only, you can index it with lowering the letters. This is one of the common pitfall where people generally fall into. Yeah. Cost of indexes, if we see, for very read heavy workloads, 90% reads, we can add more indices. But let's say it is very write heavy and it has all inserts like general real time production thing, adding indices doesn't make any sense. I mean, it makes sense for only something, adding more indices will obviously break our production only. So what we can do, nothing. From that we will transfer extra, we will have some ETL pipeline and load that into some warehouse, database warehouse, and there whenever we are building it, we can have whatever indices needed based on the analyzer's requirement or whatever the warehouse users requirement. So we'll discuss a topic about covering scan. We also call it index only scan. Here what happens is like, we never query the table. Let's say we have an index on email name, composite index, let's say, or we have something like index on email include name. Here what happens is like, it builds in index on email, and at that index it keeps just stores its name, and on this it just stores its name. But in this case here, after filtering the email, we will have binary tree in the name level also, so that is the difference. So we can, so let's whenever we do these two type of indices, let's say we are having a query something like this, select name comma email from users where email equals to some dot com x dot com. Yeah, so something like what happens here. First, where email equals to d dot com, it first uses the index and goes to the email.com. And there, what is it happening? In this case, if we in this index we are having one more name index, and again in that index it will search and it will fetch the name. And in this, what will happen, at the name, at the email only we'll be having the name, so it will return that name. It will not even touch the table. You understood it, right? So this is what we call as covering index or index only scan. So if we index only on email here and remove name, or if we don't include the name, what happens? It obviously need to fetch name from the table. So that is the main thing here. Now let's say one more thing we will discuss, that is clustered index versus non-clustered index. For clustered index, if we see, rows are stored in order with index elements. Effectively saves time. For this, if we see, what is this? Yeah. For this, if we see, index elements point to pages where rows are there, and that pages have different unordered rows. So that won't be, so increase, that will cause increased discretes. So that's why non-clustered index is low. So in for a table there can be only one clustered index, because we can order the rows only one way, right? See, if one index is ordering a rows and other index can't order the same rows, right? That's it. Yeah, thank you.